So in the previous part of the lecture, we discussed what majorization minimization algorithm is, and we discussed that we have perhaps a generalized loss function J of W, which has two components, E of Y and F phi of X, which is the error on the data set, plus lambda times some regularization function of W. And we discussed in the previous part that the majorization minimization is a mathematical concept where instead of minimizing this loss function directly, because perhaps it might be very difficult or too complex to minimize directly, or perhaps this is not differentiable convex function, so we would like to replace it with some other loss function that we can minimize easily, and that function that we select should be such that by minimizing that second loss function results in the minimization of the original loss function. So in majorization minimization, we replace this loss function with a function gk at the kth iteration of the majorization minimization algorithm. It's a function of W, and we discussed that this g of k should satisfy two properties. One, that it should upper bound the original loss function g of W, which means that gk of W should be greater than or equal to j of W for all W in the domain of function j. And second is that gk of wk is equal to j of wk, where wk is a point where we construct this function gk. So now let's see graphically what majorization minimization does, or how does it operate. So let's assume, we'll consider a scalar function. So this is our y-axis, or we can say j of W, and this is our W. So let's assume that our loss function looks something like this. Let's assume it is a convex function. So this is convex function. So let's assume that our goal is to minimize this loss function j of W. So at kth iteration, so first of all we can see that the function is non-differentiable at 2 points, and the second point also happens to be the point where the function j of W has its global minimum. So we can either try to directly minimize this j of W with, let's say, sub-gradient descent, but typically sub-gradient descent has low rate of convergence, or we can use a majorization minimization algorithm to minimize this loss function. So assume at kth iteration we have a guess for our parameters W as let's assume that this is our point Wk. So now the goal is to select a function gk that upper bounds this loss function j of W but has the same value as j of wk at point wk. So let's construct this this function gk. So let's assume like that this is our gk. It is exactly equal to j of W at, let's assume this is a differential. So it's not a kink over here. It's a smooth function. It's a smooth differentiable function with the same value as j of W at W equal to wk. So let's assume this is our function gk. So now we will minimize this loss function gk, and we can see that the minimum point is somewhere over here. So this point will be wk plus 1. So by minimizing this loss function gk, in just one iteration, we jump from this point directly to this point. So the minimizer of this function gk is, we will set it to wk plus 1. So this is a minimizer, w star for gk, and we'll set this minimum as a new estimate for the optimal parameters w that minimize the original loss function. And now we'll repeat this process. So at this point, we'll select another loss function gk plus 1, so let's assume this is what gk plus 1 looks like and has its minimum at this point. So the minimizer of gk plus 1, this is our function gk plus 1. So we minimize this function, and this minimizer now becomes the new estimate of the optimal parameters w that minimize the original loss function. So this becomes our point wk plus 2. And now here at this point, we'll select another function gk plus 2, so let's assume it looks something like this. So this is our new function gk plus 2, and we can see that the minimum happens to be at this point. So this will become our new estimate for the parameters w as wk plus 3, and we'll repeat the process again. So at this point, we'll select another loss function gk plus 4, gk plus 3, with the same value as g of w at this point. So we can see the new estimate would be somewhere over here. So we repeat this process until convergence. So this is what we do in the majorization minimization algorithm. We have our original loss function. Instead of directly minimizing this loss function, we select a function gk at point wk that upper bounds this original loss function, and it is exactly equal to the original loss function at point w equal to wk. We minimize that loss function, and the minimizer is set to be the new estimate of the the new estimate for the optimal parameters w that minimize the original loss function g of w, and we repeat this process again. So we again at that point wk plus 2, we select another function, we minimize it, we obtain a new estimate for the parameters w, and then at that point we select another function, and we repeat this process again. So this is in a nutshell what majorization minimization algorithm is. So it's a mathematical concept, and when converted into programming, it becomes a majorization minimization algorithm. So now we are ready to write the pseudocode of the majorization minimization algorithm. Of the majorization minimization algorithm. So step number 1 is we set k equal to 0 and initialize the initial parameters w 0 with an n-dimensional real vector. So perhaps you can initialize it to be a vector of all zeros. Step number 2, we select the function gk such that it satisfies two constraints. Number 1, that gk should upper bound the original loss function j. So gk of w is greater than or equal to j of w for all w in the domain of function j. Second condition is that gk of wk should be equal to j of wk. Step number 3, we minimize the function gk and then we update the estimate for the parameters. So we set wk plus 1 as a minimizer. So instead of this subscript, I should have a superscript. So I just write down, it should be superscript to denote the kth iteration, the estimate at the kth iteration. So wk plus 1 is set to be the minimizer of the function gk argmin over w gk of w. As we see in the graph as well, that we minimize this loss function gk, and then the minimizer is a new estimate for the parameters w, and then at that point we again compute a new function gk plus 1. So the next step would be set k equal to k plus 1 and step number 5 is to repeat this entire process. So go to step number 2. We can also add a convergence condition over here. So we repeat this process until convergence. And here we can add a convergence condition that perhaps checks the difference between the new estimate of the parameters and the previous estimate of the parameters. So perhaps we can have a convergence condition. We name this variable as diff, which is equal to the L2 norm of the difference between wk and wk plus 1. And we can check if this is less than some small threshold value, which can be, let's say, 10 to the power negative 3 or 10 to the power negative 4. So if this condition is satisfied, then we stop the MMA algorithm if satisfied. So that's it. That's all about the majorization and minimization algorithm. So the important thing to note in the majorization and minimization algorithm is that majorization minimization is a mathematical concept where instead of minimizing the original loss function, because perhaps it may be difficult or complex to minimize, or it may perhaps be a non-differentiable convex function. So instead of trying to directly minimize the tough optimization, the tough loss function, we replace that loss function with a sequence of easy to minimize loss functions. and that replacement should satisfy two conditions like condition 1 and condition 2, and then the minimizer of this function gk is set to be the new estimate of the parameters w, and then we repeat this process until convergence. So by minimizing a sequence of loss functions gk, we actually obtain a solution for the original optimization problem. So that's it for the majorization minimization algorithm.